Okay, so this is the sort of walkthrough of the Combined Science Trilogy Higher Tier Chemistry paper, paper 1. If you look at this first question, they always tend to start with something about the whole question. So they're talking about copper, lots of different avenues and pathways you can take with this. But we start with the graph question. And if you notice, it says give 2 conclusions that can be made from figure 1. Now this is a great question because there are loads of things you can say about it, not just 2 things at all. So don't worry. Sometimes you have to say specific things, other times you can say lots and lots of different things from a graph. It can be as simple as the years increases, so as the years increase, the mass of copper produced increases. Okay, that is a nice simple one. Always start with the x-axis and then say something about how the y-axis changes as well. So as the years increase, the mass of copper produced increases. But we can go into a bit more detail if we'd like to, and we can talk about that. We can say, let's see, I think it's about 1930. So between 1900 and 1930, the mass increases slightly. So barely, there is an increase, but it's not very much. But then after that, so that's another one. So you can say it increases. This is going into a little bit more detail, because then after 1930, the increase is rapid. And all of this is adding extra detail. Do you need all of these? No, you don't, actually. Each of these are separate points, okay? You could also say the maximum mass is 50, no, is a little bit, well, you could say the year, the maximum mass so you could say the maximum mass in 2010 is this, but you can say it actually is 15.8, and I said 15.8, but actually it's times 10 to the 9 kilograms, so I've got to make sure to use the units that are on my axes as well. All of these are separate points that you could talk about. This is a great question because there's always going to be a similar thing you're going to have to say. So it's one of those where you can sort of remind yourself of the answer. And we start with explain. That's going to tell us we need to say because or so or therefore. And alloy. Explain an alloy, essentially. They're talking about it being harder, but a lot of our explanations for alloys are actually going to be the same thing. They all link to its structure, which if you notice right at the top, they give us that clue as well, because they talk about the structure of pure copper and an alloy of copper and zinc. So what are we going to say? Well, it says you use figure 2. They're helping you out. They're telling you to use figure 2. So what we're going to start with, well, for me, when we talk about alloys, we always say different sized atoms. And they have used the term atom, so we're going to use atom as well. We sometimes say ions, and that's fine as well, but they've used the word atom, so we can use atom. And we can go into a bit more detail if we want to. We can say zinc is bigger than copper, because we can see from figure 2 that it is actually bigger. That's our first point. How does that affect the structure? Well, that means the layers of atoms are distorted. You can see in our pure copper those beautiful layers, this lattice we talk about, of repeating atoms, and our alloy is all sort of messed up. It's all over the place. Okay, so we've got different size atoms, and we can add sort of our explanatory words. So the layers of atoms are distorted, so the layers cannot slide. Okay, each bit of that is important. The 3 sort of bits I've done on lines, they're the science behind it. The explain is the so. It's you linking these together, not just writing 3 random sentences or bullet points. Okay. Our next one. Okay, so we have a bit of math, 4 marks. Now, always look for this last statement. give your answer to 3 significant figures. It means you're only going to have 3 numbers at the end of it, and it's really important because that means that's going to be one of our marks straight away. So it's sort of the maths bit is almost of calculating using a calculator. That's 3 marks, and 3 significant figures is going to be your 4th mark. So 5.25 gram sample of alloy of copper and zinc contains 13.5% of zinc by mass. Now, this is not going to be perfect, but if I know that my alloy is copper and zinc, and I know that 13.5% of it is zinc, I can work out how much copper that is. Okay, that's sort of useful. That means I can work out that it's 86.5% of copper. That's really important because they're asking me to calculate the mass of copper. Well, if we've now worked out this 86.5%, I just need to work out what is 86.5% of 5.2 grams. So I can do 86.5 divided by 100 and then times it by 5.25. Okay, this is our calculation, and this is going to give us a lovely number. Right, that gets you 3 marks. You've worked out that it's 86.5% for copper. You've then done your calculation. You've got yourself an answer. Now we need our 3 significant figures. 4.54 grams. Okay. Quite a few questions on this slide because they all link with this diagram. A student prepared copper sulfate. It's chemistry. There's lots of chemicals, and straight away, if they're preparing copper sulfate by reacting an acid with excess copper carbonate, you should have in your head, what are they talking about? They're talking about making salts. This is my required practical. Stage 1. This is our stage 1. What's the point of stage 1? It's excess. Stage 2. What's the point of stage 2? It's filtering. I don't even know what questions are, and this is how I'm going through, so I know what I'm talking about. Now, what is the formula of the acid used to prepare copper sulfate? Well, sulfate is our salt, and it is the salt of sulfuric acid, which is H2SO4. Okay, that's one of those pieces of information you need to know. You just need to know. Simple as that, really. You need to know it. H2SO4 is sulfuric acid. HCl is hydrochloric acid, and HNO3 is nitric acid. All 3 of those acids you need to know the formula for and the name. Now, why is excess copper carbonate used? If you notice, we've already said it's excess. That's important. And because we know those words, we should know what excess means. It means we've added extra. But why? Why do we add extra? What's the point? It's so all of the acid reacts. Goes back to our sort of year 7 topics, our key stage 3, where if we're adding something, the whole point of this is neutralization. So we want to get rid of all the acid so that the acid has been neutralized. So all of our acid reacts, we add excess copper carbonate to do that. Beaker N, so question 2.3, beaker N contained copper sulfate solution. Solution's important, that tells you it's aqueous. Describe how the student could produce copper sulfate crystals from the copper sulfate solution in beaker N. Now, if you go right back, it says stage 1, stage 2. You should have in your head already, there is a stage 3. We have excess in the first stage, filter in the second stage, crystallize in the third stage, and they're asking you about this practical. So, how do we do crystallization? Well, we heat our solution up. We can heat it until it boils. We don't want to boil all the water off, but we can heat it until it starts boiling, and then we leave to cool. It is important for this bit that leave to cool and crystallize. Okay, why would we know that it's crystallization and not use the word crystallize? So it's trying to use those key terms, the science. It's the science. They're testing you on your use of science and chemistry terms. So leave to cool is great, but crystallization is the method, so we're going to use crystallize. Okay, big one here. So we have a diagram with the method. We have a results table. If you notice, there's no question on this slide because there's not space for it. But this is they like to give you a lot of information in one chunk to then give you a question. Like this question, 2.4, plot the data. And you can see table 1 is there as well. Now we have, it's important to get this right, there are 3 marks. Draw a line of best fit. Now I would almost say, for graph questions, treat them as bullet points. Treat them as bullet points where each statement is going to be a mark, or at least 1 mark. So plot the data, and then draw a line of best fit is going to give you your 3 marks. So we have 1.2. This is going to be fun on this. Lots and lots of fun. I draw on this, but it should work. 2.4 and 1.7. And then 3.6. So I've already worked out that these each of these boxes on the x-axis represents 0.1, and actually on the y-axis as well. So that makes it nice and easy. They've been quite nice to us in this one. I've done a lovely there across there. You can see I'm trying to get them small. They're quite big, to be honest. I'd get them smaller if I were to draw it in pencil. It's a bit difficult with this pen. 4.8. You can see there's a pattern. You should be able to go, ooh, this looks like it's going to be a beautiful graph. Now, that's your 2 marks of getting those right. But then we have draw a line of best fit. I can tick this. I've done that first step. How do I draw a line of best fit? Well, I always think to myself before I start my line of best fit, if I had 0 mass before heating, what would be the mass after heating? 0. So I always think, does my line of best fit start at 0? Well, yes, because if I have 0 mass, then I'm still going to have 0 at the end. I haven't drawn it with the ruler. I promise I haven't drawn it with the ruler. It's relatively straight. It doesn't go through every single point, but it is showing the general trend. It's starting at 0. It's a straight line, because it is actually a straight line for this. And it's showing things. You can see that this third result here, it's not quite on the line, but that's okay. That's plotted correctly. So don't worry if not every single cross goes on the line. Okay, we have this wonderful method here. Student investigated thermal decomposition of copper carbonate. 2.5. Why does the mass of the contents of the test tube decrease in mass when copper carbonate is thermally decomposed? Lots of bits to this. I would say, in my head, if I'm talking about a decrease in mass, there's only 2 things, really. If I'm talking about a change in mass during a reaction, either gas is going to come into the reaction and react and be added as a compound, or a gas is going to be released. Simple as that. There's the only 2 options. It's going to be one or the other. Well, this one is decreasing in mass, which means the oxygen, which means straight away I know my mass is decreasing. What causes the mass to decrease? It's because a gas is escaping. Now again, I'm going to go all in. What gas? Well, I know that copper carbonate produces carbon dioxide. So actually, I'm going to write CO2 gas is escaping to cover all my bases so that they know I know it's carbon dioxide as well. Okay, our 6-mark question, our first 6-mark question. They love this sort of question because it is testing a lot of your structure and bonding within one question. They want to know everything you know about these diagrams, this table, and about structure and bonding. So I would do it as a table. Straight away, makes it easier to be able to compare, because that's the word they're looking for. It's comparing, so we're going to have on each line the opposite or a similarity so they can see. Okay, so first of all, let's see, we'll start with there's 1 Na and there's 1 Cl, and we'll start with there's 2 oxygens. That's proper year 7 basic chemistry. Count how many atoms of each. Well, the next basic thing, this is a compound, and this is not a compound, it's an element. Okay, straight away, I can get that. I can get that in from really basic. We're then going to jump to our key stage 4. There's a little bit of a jump here to what else can I see? Well, there are some phrases we try and use. We can talk about the type of bonding. So we'll start with the type of bonding. Sodium chloride is ionic. Why? Well, because sodium is a metal and chlorine is a non-metal. We could have added that from key stage 3. because that is also something to be aware of. And oxygen is not ionic. Oxygen is covalent because it's two nonmetals. We can then start talking, well, what does ionic mean? Ionic means we're transferring electrons. That's when electrons are moving from one to the other. It's not telling us how they move. It's not asking us to explain why they move. It's just that we're describing what's happening. So electrons are being moved, whereas in covalent bonding or covalent, electrons are shared. Now we can add a bit because we've got a diagram here, so we can see that sodium chloride, it's actually a 1+ ion for sodium, and it's a 1- or a -1 ion for chloride. So we can add that to the top. When your examiner is marking it, they're not going to see the exact moment at which you wrote something down, so you can come back and add something to it. Our oxygen molecule, our oxygen over here, that's not an ion. It doesn't have a charge to it, so we don't need to add the charge to that. But we can start talking about what it looks like. We can say it's covalent, but it's got a double covalent bond. It's not just covalent, it's got those two lines, which are telling us it's a double bond. Okay, now that's a huge chunk. We can now, I want to draw a line across it, we can now start talking about the structure a little bit more. This is the bonding to a certain extent. We got some more. Well, this is when these phrases come in. You see ionic and you think, ah, that's giant. And it's a lattice. Whereas oxygen, it's not. It's a simple or small molecule. So we got some differences right there. Okay, this has strong forces of attraction, and this has weak forces. But this is where it's important. Not just the strong and weak being different, but the strong forces of attraction for sodium chloride are between the ions, whereas these weak forces of attraction are between molecules. Okay, that is a difference. We are talking, another way of saying it is they are weak intermolecular forces. And that's absolutely fine. You can say weak intermolecular forces as well. But you're sort of, whereas if we say between ions and between molecules, we are really saying the difference between them. We could talk about lots of other things, but that is you don't have to say every single thing. We've talked about the structure being giant lattice or a simple molecule. We talked about the bonding, it's ionic and transfers electrons, or it's a double covalent bond that shares electrons. That is what they're looking for, a bit of both. Okay, question 4. Nitric acid is a strong acid. Tells you we're going to be talking about acids and acidity and pH within this question rather. What is meant by a strong acid? This is your definition. This is define a strong acid, and there are two aspects to this. It is ionized completely or almost completely. Okay, that's the first bit. That's what the strong bit is, and then you have the acid bit. Well, the other aspect of the acid bit, I should say, is in aqueous solution. Okay, it's only ionized completely in aqueous solution. And the next part is the other aspect of this. We have strong and weak acid is the first question, essentially, and the second one is concentrated and dilute. So this question is, and it's knowing and understanding these terms. So what is dilute? Well, it's a low concentration. Now, not a big fan of using concentration in essentially defining concentration, but a low concentration does mean dilute. So I sometimes say number or amount of acid, because it is a low concentration of acid. And the aqueous solution bit, this is the other aspect of it. It's dissolved. It needs to be dissolved in water, but it's all about the volume of water. It has to be in a fixed volume, because if you add a larger volume or a smaller volume, it's going to affect the concentration even if you don't change the number or the amount of acid you put in. Okay, so we have one about pH. Again, the previous questions in this sort of sub-questions were about acids and alkalis. This is about pH. And we have pH 1, and it's going to 2, and then the pH is going to 3. The pH is increasing, but what you need to remember is they're not asking about pH, they're asking about hydrogen ion concentration. So you need to understand that if pH 1 solution has a higher hydrogen ion concentration, which means if you're going from pH 1 to pH 3, the concentration is decreasing. Straight away, we've got to know that. Therefore, we can get rid of these bottom two. The hydrogen ion concentration is not increasing at all, it's got to decrease. And then the next bit is knowing that pH is, for every one step of pH, the hydrogen ion concentration decreases by a factor of 10. So in reality, it's not times by 10, it's divide by 10. So divide by 10 is the same thing as saying decreases by a factor of 100. That's our pH. Our other aspect, 4.4, is the ionic equation for the reaction between an acid and alkali. Again, it's a variation on your key stage 3. Your word equation is acid plus alkali makes, or an arrow, salt plus water. This is just talking about the acid aspect and just talking about the alkali. We're not talking about the salt, which means our symbol is going to be, well, the word would be hydrogen, symbol is H+. The word would be hydroxide, so that's our acid, hydrogen, plus alkali, hydroxide. Put those two together. We're not worrying about the salt this time, we're just worrying about water. And we put the state symbols in. I like to put the state symbols in. It's a good reminder that an acid and alkali are both in aqueous solutions, so they're both aqueous. They both have to be dissolved in water, and guess what? Water is water. So it's a liquid, at least, liquid water. That's one aspect. This is our equation showing the reaction between. So what is the ratio of moles? It's moles. Number of moles means ratio, essentially. So we're looking at magnesium carbonate to the number of moles of nitric acid. Well, magnesium carbonate, you need to know what the symbol, chemical formula would be, and same with nitric acid. Well, there's one of those and there's two of those, which means it has to be 1:2 ratio for those two. The student mixed some magnesium carbonate with excess. I'm looking for words every single time. Excess means too much or extra. Okay? They are not going to use the word excess unless it is important. If they're just chucking some nitric acid in, they'll just say they're going to chuck some nitric acid in. Excess means something specific. They're going to put too much or extra nitric acid in. They then add universal indicator. That's really important because they're saying what color was the solution after the addition, but it's all about the excess. It's, do you recognize the excess acid? And now we have the, do you know what red, green and blue represents or indicates in universal indicator? And red can only be correct because green means neutral, and again it's going back to your basic acids and alkalis, and blue means alkali in universal indicator. So the red one has to be correct because it's an acid, and it's red because actually it's a strong acid, which means it would have a pH of between 1 to 3. Next one, again we've got this whole method, and question 4.7 is give 2 improvements to the method. They put the bold bits in there for a reason, because the next bit is do not refer to improvements to the apparatus. It is important that you use the method, the actual things you're actually going to do to improve your method, not, oh, use a digital thermometer. It's rarely going to be, it would make it more accurate, but there are bigger issues here than a digital thermometer or an analog thermometer. Much bigger issues. The biggest issue is always the end point of a reaction. What is the independent variable and dependent? For this one, do we know? Well, it says different masses. That's going to be right at the bottom. That's our independent variable. That's fine. Can we see within this method the dependent variable? Well, we're measuring the temperature, which is great, but what do we do with these two temperatures? This is a required practical, which is why they're giving you the method, because this is a practical they expect you to have done. So if you're looking at this method and going, oh yeah, I remember this is the polystyrene cup one, isn't it? We didn't just measure the temperature. Well, we did measure the temperature, but we didn't just do that. We measured the highest temperature. Okay, we measured the highest temperature. We also calculated the difference in temperature, which they don't have. We need to measure the highest. We don't just check the temperature when we want. And for every single method, regardless of what it is, pretty much, the step I always say to include, if you're improving a method, is repeat and calculate a mean. You cannot just say repeat it. There's no point in repeating an investigation many times, unless you're then going to remove anomalies and then calculate a mean. They're really important. They go hand in hand together. They don't go separately. We then have complete a dot and cross diagram. It's 2 marks. Look at the marks. 2 marks tells you there's 2 things you need to do. And I always say ammonia, nitrogen, it's group 5, which means it's going to have 5 electrons in the outer shell. 1, 2, 3. We've used up 3 electrons from our nitrogen, but we can do that a different way. We've got hydrogen can only have 2 electrons in its outer shell, which it does, and we then count for nitrogen in its outer shell. It has 2, 4, 6, which means it's still missing 2, and that's our 8. So from a mark point of view, it's looking for that pair of electrons in each of those overlapping circles, and then your extra pair of electrons at the top. I've done crosses. You could do dots. They're equally as acceptable. Okay, 4 marks. So this is a moles question. How do I know it's a moles question? Because it tells me this, and it says calculate the mass. Straight away, I know we're going to be doing moles here. So I'm going to draw my sort of table. It helps me keep track of what I'm talking about. And it says calculate the mass of hydrogen, right? So I'm going to use my hydrogen to produce 25 grams of ammonia, right? So I'm going to put my ammonia down. I don't need to worry about nitrogen. It's not asked at all. So the mass of nitrogen is 25 grams. The MR of nitrogen, well, that's going to be 14 plus 3 times 1, which equals 17. And then I can work out my moles by doing 25 divided by 17. Okay, this is how I work it out, going through all the steps to fill it in. If I work out my moles, it's 1.47 mole. If I look on the other side, I don't have the mass. That's sort of what they're asking me for. I can work out the MR of hydrogen though. Hydrogen has an MR of 2 grams per mole. And I don't know the number of moles because I just worked out the moles for ammonia. So I'm going to get this number to count and use it to calculate my moles. This is where the big numbers come in. This is where these 2 numbers come in. I'm going to divide it by 2 and then times it by 3. And that is going to equal 2.205. And now using something I haven't written down, I've been using in my head though, is mass equals Mr. times by mole. The best way to use it. Best equation. And we use it all the time. So I'm going to do, well, I need to work out the mass of my hydrogen, so I'm going to do the Mr, which is 2, times by the mole, which is 2.205, and that's going to equal a lovely number of 4.41 grams, and that's my 4 marks. Tend to get a mark for calculating the MR, a mark for calculating the moles for our ammonia, and another mark for calculating the moles for our hydrogen, and another mark for calculating the answer. Okay, we've got our big bond energy ones where we're calculating the missing bond energy. Now, if we are calculating the missing bond energy, X, somewhere in the question it will tell us whether this reaction, numerically tell us if this is an exo or an endothermic reaction. it is telling us the energy is released is 93 kilojoules per mole greater. That tells us it's going to be an exothermic reaction. And if it is exothermic, it means our equation is going to have the total energy change is minus 93. The rest of it, I've got to work out how much energy do I need to put in, to a certain extent, what's my activation energy, and then how much is the total amount of energy going to be given out, so I can calculate the difference, which is going to be 93, or negative 93. So, what do? I use my 945, because I've only got one of those. The amount of energy in is just 940 grams, 940 kilojoules per mole, but I've also got my hydrogen, and I've got 3 lots of X. I don't know that, it's going to be 3 lots of X. Whereas my energy out is going to be 2 lots of 3, so I'm going to have 6 lots of 391 for my nitrogen-hydrogen bonds. Got 6 of those, so I'm going to do it that, and then sort of draw a line here. I'm going to equal, this is going to be 945 plus 3x, and that's my energy in, and my energy out is going to be 2, 3, 4, 6. Why do I do it like this? Because then I can put into my equation minus 93 equals 945 plus 3x minus 2, 3, 4, 6. Now, using a bit of algebra, simplifying my equation, I can then get to minus 93 equals 3x minus 1401, and then I'm going to rearrange to solve for x. It's going to end up being, because what I'm going to do on this side is I'm going to add 1401 on both sides, which is going to equal 1308 equals 3x, and then fully solve for x. I'm going to divide by 3 both sides, and I'm going to end up with my answer being 436 is the bond energy needed required to break 1 bond of hydrogen. Okay, this is your pretty standard question for an exothermic energy, endothermic energy profile diagram. We have this, and it says you should. There's lots of bold bits, complete figure 8, but it says you should, and there are 3 bullet points, and they're really important. You can tick them off as you go, because you're going to get 1 mark for each one. So when it says complete the profile line, I would always say, how do we know it's exothermic or endothermic? Well, in the previous parts of the question, it tells you. It says the energy is released. You've already worked out, calculated parts of that, so you know it's an exothermic reaction, which means the line needs to go down here for the reactants and the products. Now, as part of that, we always add this part in to show how the energy changes over time, and I've completed the profile line. Then it says label the energy level of the reactants. Now, we could write reactants and products, but for this reaction, they've given us the actual names of the chemicals, so it's better to use those. So if we say nitrogen plus hydrogen, then straight away we're going to be adding that little bit more detail here so that we know not just it's a reactant, it's a product like we memorized in class or anything else, but we actually know for this specific diagram. And that's our second point done, so we can tick that off. We have the final one, which is label the overall energy change. Well, the overall energy change is from here and it goes down, and this is overall energy change. Now, you may have learned it in different ways. Sometimes you learn it as delta H. That's not a problem. For this, I would say, because they've said overall energy change and they've put in bold overall, I would actually write those words just to absolutely fit it. Now you can see we've done all 3 things. We're missing an activation energy. They haven't asked us for activation energy, so we don't need to write that down. Okay, in the Earth, most metals are found as compounds. This is telling us straight away we're talking about metals. That can be reactivity series, that can be electrolysis, that can be extraction. There's quite a lot that can come up within this question. And we can see in these first two questions, name one metal that is found in the Earth as the metal itself. This is just testing your knowledge of the reactivity series. If you know that, you will know those last few metals that are found as metals themselves, found naturally without the need for extraction. And we have silver, gold, and you may have learned platinum as well. And actually, depending on how you've been taught that, you may have been taught copper. Now that is not the correct order for reactivity series. It's copper, silver, gold, platinum, but any of those are acceptable. Any of those are acceptable, so don't worry too much. There's not a specific one-word answer they're looking for. They're looking for four different, any of those four. Now, suggest the most economical method for extracting metal Z from an oxide of metal Z. We're going to do it English for metal Z. Okay, you can see that is more reactive than copper. Therefore, it's not extracted. It needs to be extracted. Now, I would say the most important word for this is economical. That means using the least amount of money. There are multiple ways of extracting this. We can extract this using electrolysis. We can extract this using reduction by carbon. We cannot do hydrogen because hydrogen is less reactive. Now, the more economical, the cheaper option is reduction by carbon. Heating by carbon is great. That's not a problem. You may have been taught it, heating by carbon, okay? But extraction is a method of reducing that compound, that ore or oxide of metal Z, and therefore reduction is a word that we can use to describe what's happening. We reduce something by using carbon. Here we go, we have electrolysis, but this is a specific electrolysis. This is one that you absolutely need to know, and there are set questions, really, set ideas or concepts you need to understand for this one. The first one is 6.3. A molten mixture of aluminium oxide and substance X. How do I know to underline substance X? Because in the question it says in figure 10. They are going to give you an idea. If they want you to use the figure, they will say use figure 10 or look at figure 10 or any sort of thing like that to get you to look back at that. Okay, now we're using aluminium oxide, which is our molten mixture, but one thing you need to know is the extra substance is cryolite, and you need to know that from a melting point of view and an economical point of view as well. We have the other aspect of electrolysis of aluminium oxide. What happens to the positive carbon electrode? Now, they put positive. It's really important when we think of aluminium oxide extraction. We have a positive and we have a negative, and we need to work out which goes to which. So if our aluminium is a +3 and our oxide is a -2, we should be able to work out that our aluminium is going to our negative carbon electrode, our oxide is going to go to our positive carbon electrode. So therefore, straight away we know that our oxide is going there. Now, our oxide ion is going to be oxidized. It's going to lose electrons to turn into oxygen. So we can say oxygen is produced. For those of you who are good on your half equations, you could write the half equation for this as well. You could write 2O minus 2 is going to turn into an oxygen molecule plus 4 electrons. That's our oxidation. Now, that's only part of it. Because what happens to the positive carbon electrode? We're not talking actually about the oxygen at this point. We're talking about the carbon electrode. We know that oxygen is produced there. We can say why it's going there, because of opposite charges attract. But what is happening to the oxygen when it gets there? Well, the electrode is very hot because we have molten mixture. We have a liquid metal essentially there. And so the oxygen is reacting with the carbon electrode. Okay? Oxygen's reacting with the carbon electrode. Again, we like our symbol equations. Carbon plus oxygen is going to turn into carbon dioxide. We're making carbon dioxide gas. So we can say to produce CO2. Why is that a problem? Well, we're literally using up our carbon electrode. It is turning into, is reacting and becoming carbon dioxide, which is a gas which is lost. It's lost. Okay, what does that mean? It means carbon has to be, electrode needs to be replaced. Now, I have done the half equation for oxidation. I have done the symbol equation for the oxidation of carbon as well. Those are acceptable. They also work. You are describing what's happening. That last little bit is the words you have to use of the carbon electrode needs to be replaced. That is using your understanding of equations and reactions to link that all together. Okay. Now, our next one is the formula of aluminium oxide. They've given it to us already, Al2O3, and now let's write the half equation for what happens at the negative electrode. Well, if we have said that this is oxidation, we've said this is being oxidized, we've already written the half equation for this, we know now that this is going to be reduction, because there's always an oxidation and a reduction at this level. So we can start with Al 3+, and if it's being reduced, it is gaining electrons, and that 3+ charge means it is going to gain 3 electrons, and it is going to turn into aluminium metal, the element aluminium. Okay, question number 7. We're getting towards the end of our paper now. Calcium reacts with chlorine to produce calcium chloride. Explain, so we're going to be using our so and because words, what happens to calcium atoms and to chlorine atoms when calcium reacts with chlorine to produce calcium chloride. For me, the best start is think of your equations. How are we going to write this? Well, this is a calcium atom and this is a chlorine molecule, and if those react together, they are going to form calcium chloride. It is a nice easy one. It is a nice balanced symbol equation already, which makes it easier, but now we just have to explain what happens to our calcium. Well, this is our balanced symbol equation. We can separate it into a half equation. I'm going to say our calcium is turning into calcium 2+. Well, how does that happen? It loses 2 electrons. This is what we call oxidation. This is why half equations are so useful, are so powerful, because we can use them to explain a lot of what is happening. If we use our other one, we now have chlorine. What is happening to our chlorine? Well, it's actually turning into 2 chlorine or chloride ions. If the first one of calcium was oxidation, this one is going to be reduction, and reduction is gaining electrons, which means it's going to gain electrons on this side. If all you write is this, you have answered every single little bit. Now, have you done an explain, a so? Not necessarily. So what I would say is you can add parts of that, but the first line here tells you that you have 1 calcium and 2 chlorine atoms. Now we've drawn it as a chlorine molecule, so it's worthwhile saying 1 calcium atom and 2 chlorine atoms needed. It is a molecule, it does react as a molecule, but they have asked us to talk about chlorine atoms, so we're going to talk about that. Okay, we have the ions already, we know, but we're going to talk about calcium loses 2 electrons. That's our oxidation, just putting it into words as well. And this time we're going to use atoms. Our 2 chlorine atoms gain 1 electron each. That's our little bit of adding words, not just having our equations there, just to make sure they understand that you know what oxidation and reduction is. Explain why chlorine is more reactive than bromine. Okay, this is one of those standard answers. It's either alkali metals or it's halogens. It's the two you need to understand. Don't worry about which way you do it. You can talk about chlorine being more reactive than bromine. You can talk about bromine being less reactive than chlorine. It doesn't matter which way round, you are still going to be doing the same thing. Okay? I'm going to talk about it from a chlorine being more reactive than bromine point of view, but it doesn't matter either way. You just change some of those words. So, chlorine has fewer electron shells. Okay, we can talk about electron or energy levels. We tend to talk about chlorine electron shells. You could also say is smaller. It is a smaller atom. Now, if chlorine has, remember it's an explain question, we can then do a so. Why do the electron shells matter? Well, it means the outer shell is closer to the nucleus. This is when our explanation comes in. So, what's the point? Why does that matter? There is a stronger attraction. And you need to say what that attraction means, or between what I should say. So, stronger attraction between the nucleus and outer shell. Okay, so what? What does that mean? Well, we can then say chlorine gains electrons more easily. Now, one bit I've realized I've missed, I like to add this in as well. Chlorine has fewer shells, so the outer shell is closer to the nucleus is totally correct. I'm going to actually add one right near the beginning that I always like to say that links the fewer electron shells. If it has fewer electron shells, there is less shielding. Okay, you're allowed to say shielding. Don't worry if you've looked at the mark scheme and think it doesn't say that on there. Shielding is absolutely correct. Now, I have done from why chlorine is more reactive. So we're going to add so chlorine is more reactive, just to make sure they understand that I am doing it this way around. The only change I would make is wherever it says chlorine, I'd choose bromine, and it would be bromine has more electron shells. So there is more shielding. So the outer electron is further from the nucleus. So there is a weaker attraction. So bromine gains electrons less easily. So bromine is less reactive. It is still acceptable as an answer. Don't worry. If you have a way that you have remembered it specifically and you know that, go that way. 7.3. Describe how the boiling points of the hydrogen halides change as the relative formula mass changes. It's a table question. As simple as that. Okay, so we need to talk about two things. There are two marks, not just a simple one mark. So you need to say as the relative mass. Now we can't say changes. Whenever it says the word changes, you need to be thinking it's either increase or it's decrease. It's one or the other. So as the relative mass increases, the boiling point increases. Okay? Now, you can talk about lots of different things, except what I've just said there doesn't actually apply to all of these. For hydrogen chloride, hydrogen bromide, hydrogen iodide, perfect sense. They actually do increase. Hydrogen fluoride is different. It's got a higher boiling point than everything else. So you can say, except for hydrogen fluoride. That has the highest boiling point and is the smallest. Okay, you can say it that way. It is the smallest. You can also say it is a favourite phrase, anomaly. It is an anomalous, not a result, it's a measurement. So we can't say, oh, just get rid of it, hydrogen fluoride doesn't exist. But it is an anomaly to the general trend of hydrogen halides. How did I know that the relative mass? Well, I was looking at these, and hydrogen always stays the same, so we sort of ignore that. As I go down this table, I go down group 7, which means this is the biggest, and this is the smallest. They haven't actually put that in the table. They want you to see that trend. Okay, carbon nanotubes. This is our allotropes of carbon. They are cylindrical fullerenes. That's lots of words in there. You need to understand what a cylinder is, what a nanotube is, what a fullerene is. And it says figure 11 represents the structure of a carbon nanotube. Describe the arrangement of carbon atoms. It told you in figure 11, which means you need to be describing it. You cannot use cylinder as an answer because they've already told you it's the cylinder. So what they're looking for is the individual carbon atoms. How are they arranged? Now, if you draw through any of these, you will see it is a six-sided shape. A six-sided shape, like in graphite, like in graphene. These are hexagonal or hexagons. The arrangement is in hexagons of carbon atoms. That's what a six-sided shape is. That maths shapes, 2D, 3D shapes from year 2 and year 3 of primary school are coming into this. It's a six-sided shape. Now, they're used in electronics. They've given one, which means you cannot use electronics. Give one other use of nanotubes. If anything mentions electronics, you're not going to get the mark. So if anything involves that, you're not going to get the mark. So we can have things like drug delivery. Now, we tend to talk about drug delivery from our Buckminster fullerene, but nanotubes is also an aspect of that. We can think of this nice general term, which incorporates everything basically, nanotechnology, or materials. Okay, now I've kept it nice and general. Nanotechnology and materials is so vague, but you could actually be specific, and you could say tennis rackets, you could say bikes, you could say any sort of sporting equipment, really, because we use a lot of that, and you've probably been taught about specific equipment rather than these generalities. Okay, nanotube. We haven't done many quantitative things. We've done a little bit, and they like adding a bit of Avogadro constant in there. So they're saying the number of moles of carbon in this nanotube, or they want you to calculate the number of moles. And they've given you Avogadro's number. Well, you need to know that the number of moles of anything is 6.02 times 10 to the 23. That is what Avogadro's constant is. So therefore, we need to work out how many moles. 1 mole equals this. So we need to work out how many moles it is. We can work out by doing 2,380 divided by Avogadro's number, and that is going to equal 3.95 times 10 to the minus 21 moles. It is a tiny number of moles, if that's how many atoms a nanotube contains. But it is linking that 1 mole to how many atoms there are. Well, we know that there are that many atoms, the 6.02 times 10 to the 23. That many atoms in 1 mole. So how many atoms are there? Or how many moles are there? We can do that as a ratio. We can do it as a 1 to 6.02 times 10 to the 23. And then put 2380 here. That is what we're looking for. We're looking for that missing value. So there are mathematically a few different ways you can put it. Use your calculator to do that. Now, that is a different way of doing it. I would say 3.95 as an answer times 10 to the minus 21 is what I've written down. It's 3 significant figures like they have given in the question. That is not the answer you're going to get on your calculator. So if you get a long number, it's going to have, 5 or 6 different decimal places. You can write that down, but always try and round it to 3, maybe 4. 3 significant figures is what we tend to do. So think about it. Don't just write mindlessly whatever your calculator says. Explain. We're having an explain question, so we're going to be using the so's. Explain why carbon nanotubes can conduct electricity. We've got electricity, and again it says we have to refer to bonding between carbon atoms. Which means if we're not talking about bonding, we've missed something out. What type of bonding is it? It's a covalent bond. How many covalent bonds? Well, each carbon atom, okay, this is our carbon atom. Why am I saying carbon atom? Because it tells me in the question to say it like this. Each carbon atom forms 3 covalent bonds. Okay, I'm talking about the bonding. I've ticked off that bit because I've said there's covalent bonds and there's 3 of them. So what? This is my so bit. This is my explain. So each atom has 1 delocalized electron. I've done it in the wrong place. 1 delocalized electron. So if there are only 3 covalent bonds for each carbon atom, then they're going to have a spare electron. It's going to become a delocalized electron. Why is that important? So the delocalized electrons, what do? Not just delocalized, they can carry charge. Try not to talk about current as much, because current is the rate of flow of charge. It's how fast they're going. Whereas we're not talking about how fast the current is. We're talking about how much charge, or what are they doing. They are carrying that negative charge through, and again, where are they carrying it? Not anywhere. They're carrying it through the tube, or the nanotube. And that's where it's important. Don't just say they carry charge, because electricity isn't just charge flowing, it's in a direction, which is through our tube.